Welcome to Ask and Learn.
We want to sketch the curve y is equal to x over x cubed minus 1. So in this chapter, they give us this laundry list of steps that we should follow. So we're just going to go and follow those one by one. So first, we need to figure out what our domain is going to be. Well, this is just going to be where our denominator is not equal to 0. So setting x cubed minus 1 equal to 0, we just get x cubed is equal to 1 or x is equal to 1. So our domain should be negative infinity 2, 1, union 1 to infinity. The next thing we want to figure out is our intercepts. So let's go ahead and find our x-intercepts first. X-intercept, well, this is going to be where the function is equal to 0. So 0 is equal to x over x cubed minus 1. Well, we know that our denominator can never make this function equal to 0, so we just set the numerator equal to 0. So we get 0 is equal to x, and this implies that this is also our y-intercept as well, since it's at x is equal to 0, so we don't even need to solve for our y-intercept. Next, we want to look for symmetry in the function. So rational functions aren't really known for being periodic, so we can check to see if this is an even or odd function. So in the numerator, we get negative x, and in the denominator, negative x cubed minus 1. So we can go ahead and rewrite this as negative x over negative x cubed minus 1, and distributing that negative from the numerator to the denominator, we just get x over x cubed plus 1. Now, this here is not equal to f of x, nor is it equal to negative f of x. So what this tells us, we have no symmetry, or at least no symmetry about the origin or the y-axis. The next thing they tell us to look for is asymptotes. So from chapter 2.6, when we talk about in behavior, we know that since our denominator has a larger power than our numerator, the in behavior, or as x goes to positive or negative infinity of f of x, should just be 0. So we have a horizontal asymptote at y is equal to 0. And then we can go ahead and look for our vertical asymptotes, which are going to occur where our denominator is equal to 0, which is at 1. So we need to check to the left and right of this. So it's going to be 1 from the right over 1 from the right cubed minus 1. Now, 1 from the right is still going to be a positive number. So our numerator is going to be positive. And 1 from the right cubed will be positive. And then subtracting 1, well, since we're cubing something larger than 1, after we cube it, it's going to be larger than 1. So our denominator should also be positive. So this here should go towards positive infinity. And we can use a nice little trick that since x cubed minus 1 is odd, that means our vertical asymptote should have similar behavior as an odd function with its in behavior. So since it's positive infinity on one side, that means it should be negative infinity on the other side. All right, next we want to find intervals of where the function is increasing and decreasing, and any local max or mins that may come up. So we're going to need to find what y prime is. So I'm going to go ahead and do that on another page. So we have y is equal to x over x cubed minus 1, and we're going to need to use quotient rule to take this derivative. So the way I remember quotient rule is low d high minus high d low all over the square of what is below. So x cubed minus 1 squared. Now we know the derivative of x is just going to be 1. And I actually wrote the same thing twice. I was going a little bit too fast, it seems. So I need to switch those places. So it should be x times the derivative of x cubed minus 1. Right. Now the derivative of x cubed minus 1 is going to be 3x squared, and the derivative of 1 is just 0, so we're left with that. And actually, let me go ahead and scoot all this over a tiny bit. Right, now, if you were to go through and do all of that algebra, this here should simplify down to negative 2x cubed plus 1 all over x cubed minus 1 squared. Now, to find our critical points, we're going to want to set this equal to 0. And solving for that, we would just get 2x cubed plus 1 is equal to 0, or x is going to equal to the cube root of 4 over 2. So now we can go ahead and use that information to find our intervals of increasing, decreasing, and our max mins. So this should be negative 2x cubed plus 1 over x cubed minus 1 squared. Now this function is going to be increasing when y prime is strictly larger than 0. And I went ahead and already solved this just for the sake of brevity of the video. And this should be from negative infinity to negative cube root of 4 over 2. And we know this function will be decreasing, or where y prime is strictly less than 0, on negative cube root of 4 over 2 to 1, union 1 to infinity. And we can go ahead and look at that value that we found to be a possible point of inflection. So that's going to be negative cube root of 4 over 2. Now, to the left of this value, we know the function is increasing, and to the right of this value, we know the function is decreasing. So that tells us this here is going to be a max. All right. Now, the last thing they tell us we need to do is to look for concavity, as well as any inflection points that may arise. So we're going to need to know what y double prime is to do this. So we can come over here back to this page. And so y double prime is going to be, well, we're going to need to take the derivative of the first derivative. So I'm first going to factor that negative out front. And again, hopefully I don't go too fast and actually write everything in the correct place. So it's going to be low d high minus high d low. And then all over the square of what is below. So x cubed minus 1. So it was squared before, so now it should be to the 4th power. And this negative should be out there like that. Now, to take the derivative of 2x cubed plus 1, we're going to use power rule, so we're going to end up with 6x squared. And to take the derivative of x cubed minus 1 squared, we're going to need to use power and chain rule. So first, for the outside function, we get 2x cubed minus 1. Actually, let me go ahead and scoot this down a little bit. So 2x cubed minus 1. And then the derivative of the inside function is x cubed minus 1, which is going to be 3x squared. All right. Now, if you were to go through and do all this algebra, this should simplify down to 6x squared x cubed plus 2 all over x cubed minus 1 cubed. So we can go ahead and now set this equal to 0. And doing that tells us x is equal to 0 and x is equal to the cube root of the negative cube root of 3. So negative cube root of the negative cube root of 2, I mean. And so now we have our possible points of inflection, so we'll use those in the next part to see if they actually are. So now our second derivative was 6x squared x cubed plus 2 over x cubed minus 1 cubed. So we want to figure out where this function is concave up and concave down. So the function will be concave up when y double prime is strictly larger than 0. And again, I went ahead and solved this. It would be negative infinity to negative cube root of 2 union 1 to infinity. And the function is going to be concave down when y double prime is strictly less than 0. Or negative cube root of 2, 0, union 0 to 1. And now let's go ahead and put those 2 points that we had for possible points of inflection. So we had x is equal to the negative cube root of 2, and x is equal to 0. So to the left of the negative cube root of 2, the function is concave up, and after x is equal to 0, or and between, actually no, yeah, so we already have the up, and then the rest of these intervals will be concave down, since between the negative cube root of 2, it is concave down, and after 0, it is concave down. So we actually only have that one of these points is a point of inflection. So at x is equal to negative cube root of 2, it will be concave, or it will be a change in concavity, but at x is equal to 0, it is not. So this was the last thing they told us in the chapter we should do before we start graphing. So let's go ahead and start graphing now. So the only intercept we had was x is equal to 0. We have no symmetry. We know that at y is equal to 0, or along the x-axis, we're going to have a horizontal asymptote. And at x is equal to 1, we're going to have a vertical asymptote. All right. We have a maximum at the, and let me go ahead and scoot that over a little bit more, negative cube root of 4 over 2. And we have a change in concavity at the cube root, or the negative cube root of 2. So that number is going to be to the left of that. So we should be about here. So negative cube root of 2. So I should say this is an inflection point, and this here is a max. And all right, so we have all our important points down. So let's go ahead and start by putting down our behavior around the vertical asymptote. So to the right of x is equal to 1, the function should be positive, and to the left, the function should be negative. Now, to the right of x is equal to 1, we have no important points, so we know this is just going to come down and eventually approach our axis. Actually, let me do that in green instead. So it's going to look like this. And now to the left of x is equal to 1, well, we're going to go up and first hit x is equal to 0, our origin. Now we know we need a maximum to occur at our next point, and there's going to be no other x-intercepts, so we know that it should peak around here like that. So it's going to flatten out, and then it's going to come down until it hits about the negative cube root of 2, and then change concavity. So from concave down to concave up there. So this here I think is a sufficient sketch of the graph. Something you may want to do is go back and maybe say what this y value is for the inflection point as well as for our maximum, but since we're just trying to sketch it and get a look to see what it kind of looks like, I think that's a good place to stop.